Some problems in algebra lead to inequalities rather than equations. So here were our 4 inequality symbols that we've worked with quite a bit in algebra and algebra 2. Less than, greater than, less than or equal to, or greater than or equal to. Now when you first learned how to solve inequalities, you may have been given an inequality that looked like this. 4x plus 7 is less than or equal to 19. And you may have been given values of x to test, where you would plug them in and determine if they made the inequality true or false. For example, if I gave you, I'll use a different color, if I gave you x equals 1, and you plugged in 1 in place of x, you would determine if this inequality was true or false. Well, 11 is less than or equal to 19. That is true. So we know that x equals 1 is in the solution set to that inequality. However, what if I gave you 5? If I plug in 5 in place of x, I get 20 plus 7 is less than or equal to 19. Well, 27 is not less than or equal to 19, so that's false. But that's not how we went about solving this. Let me use my handy-dandy eraser and get rid of this. You know how to solve it algebraically, so that's what we're going to do. So you would subtract 7, and you would get 4x is less than or equal to 12, and then you would divide by 4, and you'd get x is less than or equal to 3. Now, we've also talked about in a previous video, or you may have learned last year in Algebra 2, how to write the solution set in something called interval notation. So I'm going to do a quick reminder of interval notation, but we're going to do this in regards to the graph of x is less than or equal to 3. So in order to graph that on the number line, you would put a closed circle on 3, and the arrow coming from it would point off to the left. What that blue line says is that x is all the values that are less than or equal to 3. In interval notation, we wrote that as parentheses negative infinity, comma 3 bracket. We always use parentheses for infinity or negative infinity. The reason it's negative infinity is because that's the left direction on the number line. And there's a bracket at 3 because it's a closed circle. Let's talk about the rules for inequalities here for a moment. And although I use the inequality symbol less than or equal to for all of these problems, it really doesn't matter which inequality symbol you use. The way this works is still the same. Remember, for any inequality, as long as you add the same number to both sides, it does not change the inequality symbol. The same is true if you subtract the same value from both sides of an inequality. It does not change the inequality symbol. The same is true if you multiply both sides of an inequality by a positive number. C greater than 0 means positive. However, when you multiply both sides of an inequality by a negative, or if you divide both sides of an inequality by a negative, it switches the symbol. Remember the rule about multiplying or dividing by a negative. If both of your values in an inequality are positive, then if you take the reciprocal of both sides, it will also change the inequality symbol. So although A was less than or equal to B, 1 over A has to be greater than or equal to 1 over B. And then the last one, if A is less than or equal to B and C is less than or equal to D, then if you add the two inequalities, then A plus C has to be less than or equal to B plus D. So when we first learned how to solve inequalities, we learned how to solve linear inequalities. There is no one right way of attacking this problem, so I'm going to give you one way of going about doing it. 3x is less than 9x plus 4. What you can do is get your x's on the same side. So I would have negative 6x is less than 4. But I want you to notice that in order to finish solving for x, I have to divide by a negative. Dividing by a negative flips the inequality symbol, and I need to reduce that fraction. So I find out the answer is x is greater than negative 2/3. You could have also done the problem this way. If you had a teacher who said, oh, always move the smaller value of x, you could have done that. You would have ended up with the same answer. Remember, we like our inequalities to have the variable on the left. This inequality here, when you flip it, see the little alligator chomping the x? He better still be chomping the x when you flip it. So you could have also done it that way. Now, when you go graph it, where is negative 2/3 on the number line? Well, negative 2/3 is going to be 2/3 of the way between 0 and negative 1. And it's going to be an open circle because it's not the inequality with the line underneath. Since x is greater than negative 2/3, this is what the graph would look like. In interval notation, the answer would be parentheses negative 2/3, comma, infinity. Remember that open circles are always parentheses, closed circles are always brackets. Infinity will always have a parentheses. In example 2, this book calls these simultaneous inequalities. In previous textbooks that I've taught out of, they always called these compound inequalities, where there's a problem with more than one inequality symbol in it. Again, there are a couple of ways of going about doing this, and the first method I'm going to do is the way that I would do it. A lot of times students like to know the way the teacher approaches the problem. Remember, when we solve an equation or an inequality, we want x by itself. Well, this particular inequality has 3 sections. It has the part that's on the left, there's the part that's in the middle, and the part that's on the right. I want x to be the only thing left in the middle. And I'm going to use the same rules for solving equations. I have to get rid of the minus 2 first. The thing is, though, that I have to add 2 to all 3 sections. And now I can get rid of the 3 by dividing everything by 3. And I'm going to get 2 is less than or equal to x is less than 5. Graphed on a number line, this would have a closed circle on 2, an open circle on 5, and a line connecting them. This was called an AND compound inequality, because there are really 2 inequalities, and the 2 inequalities are that x is greater than or equal to 2, and the other one is x is less than 5. And wants to know where the graphs of both those inequalities overlap each other. Now, another way that you could have done this problem, I'll just get rid of this, and I also teach it this way in case it makes more sense to students. You could have started at the very beginning of the problem by creating 2 inequalities. One of them is 4 is less than or equal to 3x minus 2, and 3x minus 2 is less than 13. And then you solve each of those inequalities itself. So I would add 2, divide by 3. I would get 2 is less than or equal to x, which is x is greater than or equal to 2. And then in the second inequality, I would add 2, divide by 3, and I would get x is less than 5. So that when I went and graphed this, I would have a closed circle on 2 with an arrow pointing off to the right. I would have an open circle on 5 with an arrow pointing off to the left. And the answer is, where do the 2 overlap? Well, they overlap between here and here, and I would make my students just take their pencil and erase this. In interval notation, the answer would be bracket 2, comma 5 parentheses, because 2 had a closed circle and 5 had an open circle. Where the inequalities get trickier is when you're dealing with the nonlinear inequalities. So let's start with something that should be relatively okay. How about a quadratic inequality? Now, in order to do this, we're going to think about this problem like solving a quadratic equation. When we solve quadratic equations, we want the equation to equal 0. Well, how about we want this inequality to equal 0? In order to do that, I'm going to move the 5x, it becomes negative, and I'm going to move the 6, it becomes positive. What this inequality says is, where is the graph of x squared minus 5x plus 6 less than or equal to 0? That means below the x-axis. Now, one kind of tricky way of doing, not tricky in the hard sense, tricky in the easy sense, I guess I should say. If you graph this in your calculator, what you're going to see is something that looks like this. Now, when you see that graph, you can notice right away that the part of the graph that's below the x-axis, or less than or equal to 0, is this portion right here. Well, what kind of graphs on a number line gave us 2 points connected? Well, they were and statements. So it turns out that the answer is 2 is less than or equal to x is less than or equal to 3. Or in interval notation, brackets 2 comma 3. Well, that's the graphical way of doing it. And I'm going to honestly tell you this is the way that I would do this problem. However, there is an algebraic way of doing it, so let's talk about that. All right, so let me get rid of the graph here. The algebraic way of dealing with this problem is to go to our factoring techniques. If you factored x squared minus 5x plus 6, you should get x minus 2, x minus 3. And then what we're going to do is we're going to make ourselves a little number line here, where we're going to put 2 and 3 on the number line. The zeros of this quadratic equation are at 2 and 3. And the reason I know those are my zeros, or my solutions, is because if I do the zero product property and set each of those parentheses equal to 0, I find out that x is 2 and 3. That means that's where it hits the x-axis. So now we want to figure out where the graph is true or false. The true region is the solution to our inequality. So there are 3 parts to this problem. There's the part that's less than 2. There's the part that's between 2 and 3. And then there's the part that's greater than 3. So in order to determine what's true and false, we're going to pick a point that lies in each region. So in the first, we'll call this region 1 here. In region 1, the part that's less than 2, how about I pick 0 to plug in, just because that's an easy number to plug in. So what happens when I plug 0 into this? I'm going to get negative 2 times negative 3, which is positive 6. Is positive 6 less than or equal to 0? Well, no, it's not. So this region here must be false. Then I'm going to pick a number between 2 and 3. The easiest thing to pick is 2.5. So 2.5 minus 2 is 0.5. 2.5 minus 3 is negative 0.5. And 0.5 times negative 0.5 is going to be negative 0.25. So is negative 0.25 less than or equal to 0? Well, of course it is. So this region here is true. And then I'm going to pick the third region here. I'm going to pick any number that's bigger than 3. So why don't I pick 4? So if x is 4, 4 minus 2 is 2, 4 minus 3 is 1, 2 times 1 is 2 less than or equal to 0. Well, it is not. So this region here must be false. So the solution region must be this, which is 2 comma 3 in interval notation, or 2 is less than or equal to x is less than or equal to 3. So you might see why I like the graphing method better. There's another way of graphing it as well, where it'll give you the answer as a number line rather than just looking at the quadratic equation on your graph. So if you go to y1 equals, and you type into your calculator x squared minus 5x plus 6, and then you go to second math, you'll see a bunch of inequality symbols. Pick the less than or equal to, and then type in 0, and then hit graph. And what you'll see on your screen is you'll see this. And if you kind of look real closely at it, you'll see that there's a number line that goes from 2 to 3. Now, the only problem with the graphing calculator is you don't know if you're dealing with open circles or closed circles. So just refer back to the inequality symbol from your problem. In this case, it would have been closed circles, and that's how I knew before I did the problem on the video that this was the answer. Although I'm particularly fond of using my graphing calculator to solve this for me, or of making the little table where I determine where something is true or false, there's another way of doing this that I will show you for posterity. For this particular problem, I would have graphed it in my calculator and looked for where the graph was below the x-axis. But what you have to watch out for in this problem is that this inequality symbol is not a closed circle, it's an open circle. Now, the nice thing about this particular polynomial inequality is that it's already written in factored form, so you don't have to factor anything. So I can tell you right away the zeros are at 0, at 1, but this one's a double root, if you recall that from Algebra 2, and the other answer is at 3. What a double root means is that the graph bounces off the x-axis rather than passing through, which makes sense because it's quadratic. So on a number line, 0, 1, and then here's 3, I would have an open circle at 0, I would have an open circle at 1, and I would have an open circle at 3. So this particular problem has 1, 2, 3, 4 regions. There's the region that's less than 0. There's the region that's between 0 and 1. There's the region between 1 and 3, and the region that's greater than 3. So another way of doing this problem is to find the signs of each factor in each of those regions. So what I could do is I can start with the sign of x. We'll just deal with x because it's the first part of the polynomial. Well, let's see, I'll call this regions 1, 2, 3, and 4 just to help me out. In region 1, all the x values would be negative. In region 2, all the x values will be positive. In region 3, they're all positive. And in region 4, they're all positive. How do I know? Because once I get to regions 2, 3, and 4, they're all in the positive x region. Now I'm going to look at the next factor, which is x minus 1 squared. And I'm going to determine if in each region the answer would be positive or negative. Well, if I pick a number in region 1, so I got to pick something that's less than 0, so how about I pick negative 1? Well, negative 1 minus 1 is negative 2, but negative 2 squared is positive 4. The sign of x minus 1 squared is always going to be positive because it doesn't matter what negative answer you get, they're all going to be positive. In region 2, if I pick something between 0 and 1, like 0.5, 0.5 minus 1 is negative 0.5, but when you square a negative, you get a positive. In region 3, if I pick a number between 1 and 3, like 2. 2 minus 1 is 1, 1 squared is 1. All those numbers will also be positive. And in region 4, maybe you've already figured this out, anytime you square a number, you're always going to get a positive. So the sign of x minus 1 squared must be positive in all 4 regions. The last thing that I'm going to look at is the sign of x minus 3. Not squared. So in the region where the x values are less than 0, like if I pick negative 1 minus 3 is negative 4, so it's always going to be negative in region 1. In region 2, if I pick a number between 0 and 1, like 0.5, 0.5 minus 3 is negative 2.5. So in region 2, they're all going to be negative. In region 3, if I pick a number between 1 and 3, like 2, 2 minus 3 is negative 1. So it's also going to be negative. In region 4, when I pick a number bigger than 3, like 4, 4 minus 3 is 1. It's positive. In the last row, we're going to determine what the sign of the entire polynomial would be, based off of the sign of each part of the polynomial. How do you do that? Well, you think about what happens when you multiply these together. A negative times a positive times a negative is a positive. A positive times a positive times a negative is always a negative. A positive times a positive times a negative is always a negative. And a positive times a positive times a positive is a positive. Well, where's our solution region? Well, we want to know where everything is less than 0. Less than 0 means negative. So these must be our solution regions. One of my solution regions is from 0 to 1, and the other one is from 1 to 3. Why didn't I just put those together? Why didn't I just say it goes from 0 to 3 instead of from 0 to 1 and then 1 to 3? The reason I didn't is because of the open circle. The open circle means, oops, I should do this. They're not little lines underneath. Well, let's go back to this again. Sorry. The open circle means that the graph doesn't really exist at that point, or the solution doesn't exist at that point. So instead, what I'm going to do is I'm going to do a union of those two. We use the symbol U for union. We talked about that in a previous video. So in interval notation, I could write this as 0, 1, union 1, 3. Now, was this the only way of doing it? No. Like I said, the way that I did this in my calculator was I just graphed the polynomial. I found that the graph of the polynomial was less than 0 or below the x-axis between 0 and 1 and 1 and 3. And since I remembered from the very beginning that this was an open circle, I knew that I had to write it as two inequalities with a union. Now let's do solving an inequality involving a quotient. It's a very long process to set this problem up in order to do those plus and minus signs. So the easiest way to do this problem is to put this in the graphing calculator. Now I'm going to review that for this particular problem. In order to put this into the graphing calculator and have it tell you the solution, I'm going to go to y1 equals, and I'm going to do parentheses 1 plus x, close it, divide by parentheses 1 minus x, second math, find this, and then type in 1, then hit graph. Now, if you can't see real well, you may want to zoom in. If you go to zoom number 2, and then you have to hit enter so it'll zoom in, you'll see this funky graph that looks like this. So it's pretty clear that the answer is between 0 and 1. But if you look at the original problem, you may think that the answer is this. And it's not. It's almost that, though. So I want to go back and ask you a question. what happens when you plug that number back into the original problem? Doesn't it make the denominator 0? Absolutely it does. 0, when you plug 0 into the denominator, it just makes the denominator 1. But you can't have 0 in the denominator of a fraction, so the graph doesn't actually exist at 1. So it turns out that this is actually the answer, because you can have 0 as a solution, but you can't have 1. So that's just something you have to pay attention to. You could have also done this by simplifying this problem and doing the little plus or minus signs like I did in the previous problem, but that's a lot of work that we don't have to do when we have the graphing calculator to help us. And this is not a problem that you want to try to factor or anything. It's too much work. You can do it. We've talked about it. It involves combining fractions with a common denominator, but we don't need to do it. The other thing that you could have done was you could have typed into the calculator 1 plus x divided by 1 minus x minus 1. And then you would have found out where the graph was greater than or equal to 0. That means where is the graph of that above the x-axis? And the only place it would have been above the x-axis is between 0 and 1. But the same rules apply, which is the graph's not going to exist at 1. You can't have the less than or equal to, because the value of 1 actually makes the original denominator 0, and that's undefined.